So let's talk about integration by parts. Now, the rule that integration by parts takes advantage of is the product rule. Notice that when you take the derivative of a product of functions, you first take the derivative of the first function and multiply it by the second, and then on the right there you'll take the derivative of the second function and multiply it by the original first function. So that gives us sort of an idea, right, that maybe we could use this with integration to switch the derivative, okay? And so consider u times v. Well, the antiderivative of a derivative just gives you back the original function plus a constant, which we'll ignore here, but just for illustrative purposes. And so we end up, when we take the derivative, with this expression right there, okay? And here's what we're looking for, because if we start out with some expression that we could write in this form, okay, and we could solve for this and we get this expression there. So what is this really telling us? It's telling us that if we start with an expression of this form, we're allowed to switch the derivative from v to u, right? So here you can see this doesn't have a derivative anymore, and now the derivative is on u. So we're allowed to switch the derivative, but we have to pay a price, and that price is what's called the boundary term here, where neither of the functions has a derivative on it, and a minus sign. So okay, you start with an expression like this. You want to take the derivative off v, put it on u. You're allowed to do that, but you got to pay the price, and the price is a boundary term and a minus sign. And there goes your expression with u now having the derivative on it. We could also rewrite this in the following form. So if we, instead of having primed symbols, we could use this notation right there, and that sort of just makes it a little clearer that I want to take this d dx and put it there in front of the u instead, okay? And I'm allowed to do that if I pay the price of the boundary term and minus sign. And this parentheses closes, okay, around u, so you're not taking the derivative of the product, it's just the derivative of u, okay? So integration by parts in its basic form allows us to switch the derivative from v to u at the expense of a boundary term and minus sign, just in case you didn't catch it the several times before I said. So we could also rewrite this expression in another way, just sort of sweeping up symbols, nothing deep, okay? But if we write u prime dx as du and v prime dx as dv, then here's how integration by parts would look like. U dv is equal to uv minus v du, okay? And that's just rewriting the expression in another form. Nothing substantial is going on there. So let's take a look at an example. So in this example, okay, we want to integrate that expression. Now, first off, why would I get the hint that I should probably use integration by parts? Well, it's really easy to integrate e to the power of 2x. It's also easy to integrate x, right? But together, it becomes a little complicated, and trying to use substitution there would not work, okay? But if I could get rid of that x somehow, then integrating e to the 2x is easy, right? And this is what sort of gives us a hint. What if I write e to the 2x as dv, okay? Why would I choose this to be dv? Why would I choose e to the 2x to be dv instead of x being that? Well, integrating e to the 2x is easy. That's number one. Number two, taking the derivative of x gives you 1. So it simplifies the expression. So here's what I'm going to do. I'm going to choose my original functions. U is equal to x and dv is equal to e to the power of 2x dx. Okay, and now my new integral will have v du, right? And so du, if u is equal to x, du is equal to dx. You just take the derivative of u with respect to x, and that's equal to 1. So you'll have du dx equals 1, and you just multiply both sides by dx, and you get du equals dx. Okay? Now, what would then v be? Well, if dv is equal to e to the 2x dx, integrating that, you'll get that, and ignoring the constant because we'll just put an overall constant at the end, you'll get the integral of e to the 2x is just 1/2 e to the 2x. Okay, and so that's what we'll get for v. And again, we ignore the constant until the very end and just add it to the final expression. Okay, and so that's really nice. Let's see what we were able to do with that. So here's our original expression with dv and u. Okay, I want to trade a derivative for e to the on e to the 2x to a derivative on x. Got to pay my boundary price. My boundary price here's uv. Okay, and in this expression here, I'm just going straight forward by the formula. And so here's my boundary, uv. You can see here are uv minus, and now v du. Okay, and there's that integral. Okay, now it's really easy to integrate e to the 2x, and I end up with this expression here, simplifying it, and I get this. Okay, we could also see this in another form, so I could have just written it in another form. Okay, so some people prefer to just use the box and write it out, and that's very useful for when you first start learning this section. On the other hand, once you get used to it, what you could do is think about integration by parts as sort of factoring out a derivative from one expression. So here I'm going to quote factor out, okay, d dx. I'm going to factor out a derivative from e to the 2x. Okay, and you could take the derivative of 1/2 e to the 2x. You'll get back the original expression of e to the 2x. So I quote end quote, factored out a derivative. And now I want to take my derivative, and instead of taking the derivative of 1/2 e to the 2x, I want to switch. I want to take the derivative of x instead. Well, I can do that. I'm allowed to do that, but I got to pay a price. The price is a boundary term, which involves the 1/2 e to the 2x and x. So that's the price. That's my boundary term. X 1/2 e to the 2x. Okay, that's my boundary term, and the minus sign. Okay, and so now I'm allowed to switch the derivative, and now the derivative is applied on x instead of 1/2 e to the 2x. Okay, and then you end up with the same steps. You'll end up, if you simplify, with this expression right here, and we're at the same place. Okay, I just wanted to show you an alternative way of thinking about it, the sort of idea of factoring out a derivative. On the other hand, this tends to be easier and more formulaic when you first learn about integration by parts. So let's now look at another way we could use integration by parts. Okay, so here we start with that integral right there. Okay. Now, why would I want to use integration by parts there? I mean, if I keep integrating or taking derivatives of e to the 2x, I'm going to keep getting expressions that are proportional to e to the 2x. If I keep integrating or taking the derivative of sine x, I get this cyclical pattern where I'm going from sine x to cosine x to minus sine x to minus cosine x. And so it's not exactly obvious that I would make my expression easier by taking derivatives and integrals of the product of these functions. On the other hand, notice what I was just saying, that there's a cyclical pattern there. So if I do keep integrating, say, sine x and whatever comes out of it, then I could get back sine x. Okay, I can get back an integral that looks similar to the first integral. And if I do that, I can algebraically solve for the integral that I want. And so we keep using integration by parts here until the integral that I started with shows up again, and I solve for it algebraically. That's a strategy that we will take with integration by parts being applied this way. So let's get to work. So I'm going to go ahead and choose u to be e to the 2x and dv to be sine x dx. And what that means is that I'll be integrating sine x and taking derivative of e to the 2x. Okay? And so when you integrate sine x, you get minus cosine x. And here's my boundary term, the minus sign that I pay for. And I get to take the derivative now of e to the 2x, and I get 2e to the 2x dx. I end up with this expression. Okay? Now, the integral of e to the 2x cosine x doesn't look like this. But what if I do the same thing or a similar thing again, and I take the integral of cosine x again, or the trigonometric function again? So let's do that. And so here's what I had from the previous step. I'm going to choose u2. Now I'm doing another integration by parts, and I have a subscript of 2 to show that I'm doing this again. And now focusing in on what's inside the square brackets, I have a boundary term, and this sine x came from integrating cosine x, and I get to take the derivative of e to the 2x and have sine x, okay, the integral of dv. So just following the formula above in a straightforward way. And simplifying, okay, so we just simplify here, and this is what I was looking for right here, okay? Right here is what I was looking for. This expression is exactly the original integral, e to the 2x times sine x, okay? This is, so here is exactly that integral, okay? And see it, so I write them now in red to make that clear, okay? And you could see that they're both the same. And what I do is then solve for the red function, integral. I solve for it algebraically. So I'll move negative 4 times the integral to the other side. Okay, so I add plus 4 and the integral to both sides, and I end up with that expression there. Okay, and the left-hand side is then 5 times that integral that we started with, and that should be equal to this. Then now finally divide by 5, and there it goes. Add the c, of course, we put that in by hand. And here goes our final integral right there. So we were able to take advantage of the cyclical properties of sine x to get back the original integral. Okay, and also this worked because of the fact that the integral of e to the 2x also is gives you back an expression that's proportional to what you started with. E to the 2x, integrating it gets 1/2. E to the 2x, or taking derivatives of it, would give you 2 to the 2 times e to the 2x. Something to note here is, some of you might be thinking, well, you could have also switched this around and kept taking the derivative of sine of x and the integral of e to the 2x instead of the reverse. Okay, so you could have started with e to the 2x dx being dv1 and u1 being sine x. And I encourage you to go ahead and try that out for yourself. And indeed, you will get back a cyclical expression, and the final answer will always be the same. I should also point out that sometimes, here I just wrote it in red and kept it very clear, but sometimes you'll see people just substituting, instead of writing it in red, they'll just write I. Okay, so they'll write I wherever you see a red here. They'll just write the expression I to represent the integration and solve for I algebraically. That's just, for some people, it's easier to solve for I than solving for an integral expression. Okay, well, what about if we have a definite integral? Okay, works very similarly. Okay, we end up with the same form of the formula, except now we have bounds, okay, of a, b there. All right, so let's do this integral natural log of x from 1 to 2, okay? And here, we don't see a product of function, right? Where's the second function? Well, look, taking the derivative of natural log of x, that's 1 over x. So maybe I could get away with trying something there. And although it's not explicitly written, natural log of x is being multiplied by 1. So why don't I write this natural log of x dx as natural log of x times 1 times dx, okay? And I'll choose dv to be 1 dx and u to be natural log of x. And what does that mean? That means I'm going to want to integrate 1 dx, and that's pretty easy integral to do, right? You just get x. And I'm going to take the derivative of natural log of x. So I'm going to switch the derivative from 1, right? So it's going to, and the derivative of x is 1. So I'm going to switch the derivative of that to natural log of x. And so you'll get this expression. And again, here I encourage you to just use the formula to think about this and write the using dv's in a box, such as I've done before. And you have the bounds, okay? And we get to now write v du instead, and you could see x times 1 over x, well, that's just 1, so it's really easy to integrate that. And we get this final expression here, simplifying, and you get that right there, okay? And so if I want to show you also the alternative way that I showed you above, that once you get pretty comfortable with integration by parts and you no longer want to need to write out the box, okay, which it does take time, here's how that would look, okay? So I have a 1 over there times 1, and I'm going to, quote, factor out a derivative from 1, which really just means integrating, right? And then I want to switch over dx from x to the natural log of x, and so I get to do that, but I got to pay a price. The price is a boundary term with the 2 functions and the minus sign. And now I get to switch out. Now I get to switch out the derivative. That's a dx there. It's just sort of getting clumped up. Okay, well, x dx, that should be there, okay? So if we write this out again, we'll have d dx natural log of x times x dx, and these two functions are being multiplied, natural log of x and x. It's not, that second x is not in the natural log. And the derivative of natural log of x is 1 over x, and that's pretty cool. This thing cancels, okay? The x and 1 over x, and you get which integrating gives, and I switched over the x and natural log of x so I don't have to keep writing parentheses, and so you'll get x plus this arbitrary c. And again, to apply the bounds is pretty straightforward. You could just write bounds. So I did there the indefinite integral, but if you just apply bounds at the end too, like if you had 1 2 1 2 1 2, you would get the same answer that we had above. So that also works for the definite integral, okay? Okay, you could see that it's pretty straightforward to just put in the bounds. And so now we started with an expression that didn't seem like a product at all, but with some ingenuity, which we can gain by doing a lot of practice problems, then we could see that there was a hidden 1 there, and we solved this integral with this new technique called integration by parts, which takes advantage of the product rule.